Okay, so why don't we begin just by doing some practice problems. Find the inverse of 3x3 matrices. So if you recall from last time, well, by the definition of the inverse, the inverse of a matrix is, if it exists, is some matrix where if you multiply by that matrix, you get the identity back. So we found out to solve this type of problem is equivalent to essentially using matrix algebra to cancel out A. And by doing that, we use elementary matrices. We can use elementary matrices to multiply A, that multiply A. Such that it cancels out A, and you're left with the identity matrix. So if you can find these elementary matrices that do this, then you have found the inverse. This would be the inverse, A inverse. So we saw that doing this process of multiplying elementary matrices to get the identity is equivalent to putting a matrix in. So this process of multiplying elementary matrices so remember, elementary matrices are the row operations.
Yeah.
To get identity is just finding the reduced row echelon form. So knowing that, what we can do is we can translate this whole, complicated matrix algebra into an augmented matrix. So AX equals I translates into A augment I. And then solving the system equates to solving by using row operations. So this process of multiplying on either side by these EIs is equivalent to row operations. So doing our row I plus alpha row J, that stuff, this is some elementary matrix. So when we do the process of putting this into reduced row echelon form, so we would get the identity on our left part of the augment and the series of elementary matrices on the right. And we had said that whatever this X is exactly A inverse. So whatever is left over on your right-hand side in your augment after putting into reduced row echelon form will be the inverse. Okay, so let's do that for, oh yeah, so anyway, just any questions on that? I'm gonna get the kind of the idea. So what we can do when finding inverse, we can just take the matrix and augment with the identity, and then put the left-hand matrix into reduced row echelon form. So let's do that for this first matrix here. So okay, so we want to find the inverse. So step one is augment with identity. So we have 1, 1, 2, 2, 1, 1, 3, 1, -1. We're augmenting it with the identity matrix. Okay, step two is find the reduced row echelon form. Okay, so can someone say first step? Good, yeah. Row 2 to row 2 minus row 1, and row 3 to row 3 minus 2 row 1. So by doing this on both sides, we're getting the product of that elementary matrix on the right-hand side. So we have 1, 2, 3, 0, -1, -2, 0. What is that? -4. So this is -3. And then this is -6. So that makes this -7. Okay, so doing the row operations on the right-hand side. So row 2 minus row 1 is -1, 1, 0. And -2 row 1 is -2, 0, 1. Okay, any questions on that first step? Okay, so what would our next step be? Yeah, probably minus row 2. While we're here, why don't we subtract out row 3? Just get rid of all negatives. So one thing to keep track of is that remember that you need to do all these same operations onto the right-hand matrix too. I think a common mistake is to kind of forget about the right-hand matrix, but it's the most important one. Okay, questions on that one? Okay, so what would our next step be? Oh, this is just a quality of life operation. You don't need to do this, but it's just to get rid of negatives. Just to get rid of negatives. Yeah, just because it'll be easier to work with. So it's easier to mess up if you have too many negatives. Yeah, so then you want to do, well, you want to do minus, right? So row 3 to row 3 minus 3 row 2. So remember, the main goal is to put the left-hand matrix into reduced row echelon form. So we have done that a lot of times. So whatever works best for you. Okay, so minus 3 row 2, this makes -1. Minus 3 row 2, this makes +3, and negative. Okay, any questions on how we got here? Did everyone agree with the computation? Okay, so remember, we're trying for reduced row echelon form. So yes, now we eliminate upwards. So now we take row 2 and do row 2 minus 2 row 3. And we also do row 1 to row 1 minus 3 row 3. So we have 1, 2, 0, 0, 1, 0, and 0, 0, 1. Okay, so row 1 minus 3 row 3. Row 1 minus 3 row 3, so that makes 4. Negative 3, positive 1. Okay, row 2 minus 2 row 3. So this is plus 2 is positive 3. Minus 2 row 3, so this is negative 1 minus 6 was negative 7. And then minus 2 row 3, positive 2. Everyone agree with that? Okay, and then what's the last step? I believe so, yeah. Negative 1, oh, thank you. I don't know why there's negative there. Positive 3, negative. Thanks. And then what's the last step for reduced row echelon form? Yeah, get rid of the 2. So that's row 1 goes to row 1 minus 2 row 2. Okay, so that is minus 6. This is negative 2. So this is plus 14, so that's positive 11. Minus 4, so it's negative 3. And then the rest is the same. Okay, so now we have Ix is equal to A inverse. What's row 1 minus 3 row 3? What's that for? Sorry, I'm putting the left into reduced row echelon. Oh, yeah, sorry, row 1 minus 3 row 3 was from this one to get rid of the 3. Yes, so that is doing, so row 1 is, so I have 1 minus 3 times negative 1 in the first position. And that makes 4. Second position, oh. Okay, so this is negative 9 and positive 3. Okay, so that's wrong. Thank you. Okay, so the rest is okay, right? Okay, so we have so minus 2 row 2. Plus 2 is 6. And then minus 6, negative 15. And then plus 2 is 5. All right, is that better? Yeah, thank you for spotting that. Yeah, don't be shy to point out my mistakes. All right, so so barring any computational errors, This is A inverse. So whatever original one was. Okay. How do you check it? How do you check your work? So for example, the first thing we did, or I did, was incorrect, and I got something different. Right, so you just multiply both out. So if you take the product, good, yeah. If you take the product, you should get identity. If you don't, you made a mistake. So either in your multiplication or in finding the inverse. Yeah, I mean, we'll talk about how the determinant plays a role here. But actually, yeah, as we talk about the determinant, it's a number that determines if a matrix has an inverse. So the determinant of this thing would be non-zero. That'd be right now all you could say about the determinant. But hopefully we'll cover that today. Determinant of the 3 by 3, at least part of it. All right, any questions on that problem? Again, sorry for any computational errors. Okay, so let's do the other one. This one here. 1, 3, 5, 0, 1, 1, 1, 2, 4. So let's find inverse. Okay, so let's do it. 1, 3, 5, 0, 1, 1, 1, 2, 4, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, what's your first step? Well, here's the first step. I augmented with identity. So what's your first step in putting this into reducer echelon form? Good. Row 2 to row 2 minus 3, row 1. At the same time, you can do row 3 to row 3 minus 5, row 1. Okay, let's do it. It's 1, 0, 0. Then we get 1 minus 3 is negative 1. 1, and then minus 5 is negative. Okay, on this side, we have 1, 0, 0, negative 3, 1, 0, and negative 5, 0, 1. Okay, what's your next step? Row 3. Well, I don't need to negate row 3, but I can just do the normal operation, right? Row 3 minus row 2 is 5. Okay, so what do you get when you do row 3 minus row 2? Look at it again. Row 3 minus row 2, it's 0, 0 something, yeah? 0, 0, not 1. It's not going to be 2 either. -1 minus -1. Yeah, okay, keep track of the negatives. That's going to be a lot of mistakes will happen there. Get a 0. What does that mean? Oh yeah, it's fine that, so at this point, it's okay that even though these things are the same, it does not necessarily imply that these things will be the same. Is that what you mean? Yeah, that's okay. Right, because you're doing different row operation. You're doing the same row operation put to a different matrix, right? Yeah, so why does it imply that you can stop here? Right, we can stop. There is no way to get identity, right? Any matrix that has a 0 row or 0 column can never be row equivalent to I. That makes sense. There's no way to turn that into a 1, right, without changing the other entries. So what does this mean about the inverse? Correct, it means there is no inverse. So that means this matrix, which I keep on forgetting, 1, 3, 5, 0, 1, 1, 1, 2, 4 is singular. Right, that means does not have an inverse. All right, questions about that? So it's not row equivalent to identity, which means it cannot have an inverse. So this has no solution. There's another way of expressing that. Okay, so any questions about that? A little better with finding the inverse. So again, we've been doing row reduction this whole semester. So the only thing new about finding the inverse is just knowing how to set it up and how to interpret, the result. But the method is the same thing we've been doing all semester. Okay, so any questions on the inverse? Okay, so let's talk about this LU factorization. Okay, so this might come in handy later. The idea is the fact that we'll show if a matrix can be put into row echelon form using only type 2 or type 3, then, this is n by n, of course, then the matrix can be factored into a lower triangular matrix times an upper triangular matrix. Can someone give me like just a intuitive definition of upper and lower triangular? What does it mean for a matrix to be lower triangular? So this is what we covered a little bit last time. Yeah, so so in the, oh, so it's the other way around. So for lower triangular, it means the interesting stuff is in the lower part and 0 is in the upper part. So upper is 0 is in the lower part and then stuff in the upper part. So the defining characteristic is the zeros. You can still, this stuff could be zeros here and it would still be, for example, an upper triangular. So it's precisely where the zeros are placed, where zeros are placed. So a diagonal matrix is both upper and lower. So you have stuff on the diagonal with zeros on either side of the diagonal. Okay, so questions on that definition? So it's a very like not mathy definition, right? I'm using the word stuff and just kind of drawing some pictures. Yeah, type 1, that's row swapping. So yeah, yeah. So diagonal matrix is everywhere is 0 except for possibly the diagonal. Yeah, let's talk about row swapping. What is row swap? So for my 0, 1, 1, 0, is that a triangular matrix? So look at those definitions. Yeah, no. So the requirement for a triangular matrix, so this is the diagonal here, right? One of these would need to be a 0 for it to be triangular. Right, but they're both non-zero, so it can't be triangular. So row swaps, that's one reason why we disallow for type 1s. Because a row swap is neither upper, lower, and it's not a diagonal matrix. Okay, so let's do a definition that is a little bit more mathematically rigorous. So the idea is, what was the main definition of a lower and upper triangular matrix is the placement of the zeros. So when thinking about indices, which entries are 0? Can you kind of give like, so for Aij, can you say which entries should be 0? What's the relationship between I and j that you want to be 0? Think about like, what's the relationship between I and j in all entries to the right of the diagonal? Or how about this? Can someone say, what are entries on the diagonal? What must be true about ij for entries on the diagonal? Right. So diagonal matrices, on the diagonal, it's Ai j, where I is equal to j. So now, how could you characterize? Yes, yes. So you could say that Aij is equal to 0 for j greater than I. Right. So if the column is the column coordinate is larger than the row coordinate. Does that make sense? So the column coordinate is greater than the row coordinate. So for example, A1, 2 is in the upper right part of the matrix. Does that make sense? So for lower, for what was that? For upper triangular, it's Aij equals 0 for which? Other way around, yeah. So for j less than I. And diagonal, what would be diagonal? Aij equals 0 for so what entries must be 0 for a diagonal matrix? So j equals I is where stuff could be non-zero. So it's for where j is less than I and for the positions where j is greater than I. So yes, so another way of saying that is for when it's just not on the diagonal. So for where I is not equal to j. Okay, so let's do a proof. So let's say D1 and D2 be diagonal matrices. Show D1 times D2 is diagonal. Okay, so maybe for the sake of indexing, let me just say A and B. So A times B. Okay, how would you do this? So we just gave you the entry definition of a diagonal matrix. So it's where the entries that are not on the diagonal are 0. So how would you prove that the product is diagonal? So what can you say about the ijth entry of the product? What do you want it to be? So we want ABIJ to equal 0 for I not equal to j, right? That would be the goal, to prove this. Does that make sense? That would imply it's diagonal. So what is ABIJ? Do you know what it is? You don't have to give the whole thing, but would you know how to write that? Remember, it's not just the product of A and B, right? It's matrix multiplication. Feel a bit more involved of a definition. So it's like a sum, right? It's the sum from k equals 1 to n of a, I, k, b, k, j. It's important to remember that. Does everyone remember this? Okay. So what can you say about these entries? So remember, A and B separately are diagonal. So look at that sum definition. There are a lot of zeros, right? So we can even write it out, right? So we have A, I1, B1J plus A, I2, B2J, and A, I-N, B-N-J. So what entries are 0? Remember, the A and B represent entries of big A and big B. So for example, do you know anything about AI1? So diagonal, remember diagonal means everything but the diagonal are 0. So the only not, so another way you could say Aij is only possibly, it's okay, only possibly non-zero when I is equal to j. So, for example, if I want to look at AI1, is that 0? When is it not 0? Remember, A is diagonal. So if A is diagonal, AI1, when is it equal to 0? So recall, diagonal matrix, Aij is equal to 0 if A does not equal I does not equal j. So AI1 equals 0 when? If, well, our j is already 1. So it's equal to 0 if the I is unequal 1. Right? So I have my row and my column. Yeah, so one is already defined for us to be the column. So this is saying that, so even just think about the first column in the diagonal matrix. So here's a diagonal matrix, and look at the first column. What is the only entry that's possibly not 0 is A1, 1, but the rest must be 0. That's the idea. So what is the only entry of A? So of all these A's, Which is the only one that's possibly not 0? Well, look at, so in all these I1, I2, it's only possibly not 0 when it's like I, right? So of all the A's, the only possible non-zero so of all these A, I, K, the only possible non-zero is when K is equal to I, right? Okay, so let's rewrite the sum. A, B, I, J. So if the only non-zero possible term is when K is equal to I, can I rewrite this sum? So for example, like if 1 is not equal to I, then this term goes away, right? If 2 is not equal to I, then this term goes away, it's 0. So what's the only term that survives in this whole sum? So the only surviving term is when K equals I, right? So let's write that. So let's plug in K equals I. We have A, I, and B, I, J. Right, I'm plugging in K equals I. And all the other terms will be 0, right? Because that's what we just said. Since A is diagonal, all the other terms will be 0. Sure, let's do an example. It's okay. We can ground our proof in an actual example. All right, so let's take, so when you do the first, for the first entry in the result, we have 1 time, well, actually, let's do it by A's. So the entry in the product would be, yeah, actually, let's do, so we know A, B, I, J is equal to AI1, B1, J plus AI2, B2, J plus AI3, B3J. All right, sorry. Does that make sense for a 3 by 3? That's the formula for a 3 by 3. The ijth entry in the product is this sum. So if I'm only looking at the A terms, and think about I, what is the only possible, there's only one term that survives, right? Is whatever terms in the diagonal. So think about AI1. AI1 is anything in the first column, right? AI2 is anything in the second column. And AI3 is something in the third column. So for I equals 1, I'm looking at the first row. For I equals 2, I'm looking at the second row. For I equals 3, I'm looking at the third row. So the only surviving term here is AII, right? For example, if I equals 1, then these would disappear. Does that make sense? If I equals 1. If I equals 2, these terms would disappear, right? If I equals 3, then these terms will disappear, etc. So we don't know what I is, but we do know that whatever it is, the only term that doesn't disappear is whatever AII is. So there's only so in all three cases, we're only going to have one term left. There's going to be no adding. So then in the B term, the row index will also be I. So that's just in the case of the 3 by 3. So the analog in the n by n is that, of all these terms, only one thing is going to survive, is whatever term is in the diagonal in A, which is AII. Then we have BIJ. So is the jump to the n by n better? Okay, so what can we say about the result here? So this is the ij entry in a product where A is diagonal. So we haven't yet invoked that B is diagonal yet, right? So when is this 0? So think about B now. So ABIJ is equal to AII times whatever BIJ is. That's what we just established. So if we know that B is diagonal, what can you say? So what do you know about BIJ? When is BIJ equal to 0? So the J stayed, right? Where does the substitution lie? It lies in subbing in for K, right? But yeah, I see it, yeah. It's only non-zero for, yeah, so when J equals I, then this thing is non-zero. Yeah, so B is diagonal, so these entries are 0 for I not equal to J. So that means that, yeah, ABIJ equals 0 for I not equal to J. Right, the only possible way for this to be non-zero is like BII, like you said. Okay, so any questions on that? And is it a bit better? So now let's try to do the same thing, but for lower triangular. Lower times lower is lower. Okay, so let's do the same idea. It's going to be maybe a little more difficult because it's not just equals. there's more possibility, there's less possibilities for things to be zero. So let's recall what lower means. Aij equals 0 for what? For j is greater than I. So recall. So column is greater than row is in that upper right quadrant or upper right half of the matrix. So the same thing is true for Bij. Bij is equal to 0 for j greater than I. Okay, so let's do the same thing. Let's look at the product. Abij is equal to the sum from k equals 1 to n of a I k b k j. All right, so I'm going to give an alternate definition for lower triangular, but it's equivalent. So here's an alternate definition. Can someone give me a letter to use for an index? S, I like it. I plus S is equal to 0 for S greater than 0. And of course, let's say maybe S is a natural number. Does that make sense as an alternate definition? You see how those two are the same? So you have I plus, how do you compare I plus S and I? Would you agree that I plus S is greater than I? Yeah, so that satisfies the j greater than I thing. And would you agree that j greater than I is essentially saying that, well, I is, or j is just some I plus some number, right? That adds up to, or S is the number that you add to I to get j. So when I want to think about lower triangular, what I really want is A, B, I plus S is equal to 0. That's what we want. So instead of J, let's put I plus S. So I'm only looking at the upper right entries. Well, not I plus S because I'm doing a product. Okay, everyone see the transition from J to I plus S? Okay, so let's look at this product. Can you describe for me values of K that make this 0? So for example, for AIK, what must K be for this to be 0? So remember, A and B are both lower triangular. Yeah, when K is greater than I. Yeah. How about, so for B, K, I plus S equals 0 for what values of K? So remember, B is also lower triangular. Right, you want I plus S to be greater than K. When K is less than I plus S. So for what values of K is this term 0? So for K, that is less than I plus S and greater than I. This thing is that term of K is equal to 0. All right. So what does that mean about ABI I plus S? So here's a, how about this? Is there any possible way for this thing to not be 0? Let's like write it out. So we have like AI1, B1, I plus S, AI2, B2, I plus S, and then A, I, N, B, N, I plus S. So all right, so for the first one, the only possible way for this to be, so like maybe take A for example, AI1. What's the only possible way for this to be, so remember we're in the first column. What's the only possible way for this to be, well, that one doesn't make too much sense. Okay, so would you agree that B1 I plus S, that has to be 0? Would you agree that this is equal to 0? So I'm looking at the first row. Yeah, the only possible non-zero entry is the first one, B11. But even if I is equal to 1, S is bigger than 0, so that has to be 0. So going down, so in the last term here, would you agree that AIN has to be 0? So I'm on the ith row, and n is the last entry. Would you agree that that has to be 0? Yeah. Well, only if I equals 1, except for I equals n, right? Except possibly I equals n. So, so that would go away. So when you're so canceling out these terms, you know, we come to this the statement that for some fixed I and I plus s, that oh, sorry, I shouldn't have. Sorry, I think I missed it. This is an or statement, not an and statement. So yeah, so think about I and I plus s. So this is saying that when k is greater than I, this thing is 0. When k is less than I plus s, this is 0. So since so either k greater than I makes this 0, or k less than I plus s makes this 0. So do you see how that implies that for all k it's equal to 0 then? Sorry. Right. So there's two conditions, right? For yeah, I made a mistake there. That would be an and statement, right? So it does not need to be both greater than I and less than I plus s. That was just my mistake. It's an or statement. So it could be greater than I plus s. Is this thing that's stated in the first case, right? If k is greater than I plus s, it's still going to be 0. So that was my mistake. I treat this as an and problem rather than an or problem, right? So for all k, the term is 0. Right? So that means everything is 0. Yeah, my apologies. So forget, yeah, the I less than k less than I plus s was not correct. That would be treating it as an and statement. But let me think of this number, this number line here. K, this implies k greater than I, then equal to 0. And this implies k less than I, then equals 0. So if you put them together as an or statement, every single k would equal 0, would make the term 0. Okay, sorry, so is that better now? Okay, so that means that AB is lower triangle. Okay, so why talk about all this? And you can do the same for upper triangular. You can do the same similar proof. So why talk about this is that elementary matrices that are type 3 are either lower or upper triangular? Can you tell me the type 3 matrices used for Gaussian elimination are they lower or upper, do you think? So remember, this is putting it into row echelon. So it's actually the other way around. They're going to be lower. So when you do row I to row I plus A row J, what when you put something in row echelon form, what do you know about that pivoting row? Is that going to be closer to the top of the matrix or closer to the bottom of the matrix? So when you use a row to cancel out another row in Gaussian elimination, this row I is going to be further down, right? I is greater than J in for putting when you put into row echelon form. Oh, sorry. Yeah, into row echelon. And just for example, the first thing you do is row 1, i.e. row 1 or row 2 to row 2 plus 4 or minus 4 row 1. Where you're always using you're always using a smaller row to delete bigger rows. Does that make sense? You're always using the smaller indexed row to delete a larger indexed row. Okay, so now if that's true, what do you know about a type 3 operation row I to row I plus A row J? Is that upper or lower? So let's say if I is always greater than J, where does A go? So here's row I here. In your elementary matrix. So let's remember what type 3 matrices look like. What do type 3 matrices look like? Where does the A go? So for example, what's the row operation that does row 2 minus 4 row 1? What does the second row look like? What's row 2 minus 4 row 1 look like? 0, 1, 0 wouldn't do anything, right? So if I want to do row 2 minus 4 row 1, negative 4 goes somewhere, right? Makes sense. So I'm doing this operation. Row 2 to row 2 minus 4 row 1. What is the elementary matrix that does that? So I gave you the first and third row. Remember, those are the ones that don't change their identity. So what does the second row look like? Just a couple classes ago, remember that you put a -4 in the first position and then 1, 0. It's okay. So this is the elementary matrix that does row 2 minus 4, row 1. This matrix here. The question is, what does that look like when you do row I to row I plus A row J? So the idea is that in row I, everything else looks like identity, except for row I. So just as -4 was placed in the first position, because we're doing something about row 1, where does A go? A goes in the jth position. Now the question is A over here or is A over there? It's on the left. Why? Because what's this position here? What is it? What position is that 1 in? Remember, this is an identity matrix, right? This one is on the diagonal. And if we're in row I, yeah, it's in position I. Ith position. So this A must be, this is in the jth position, must be to the left. Okay, so the claim is that when you do type 3 operations for row echelon form, so type 3 for getting a matrix into row echelon form, is always lower triangular. So do you agree with that? So that's what we just said. The position of the A is always right to the left. So this is always lower triangular because all the above entries are 0. So what does that mean? If I have A times type 3s equals row echelon form, maybe they're type 2s. What type of matrix is this? So we would just establish that all elementary matrices that are used to put a matrix into row echelon form are lower triangular. So this must be lower triangular. Now, what type of matrix is row echelon form? It's upper. So what we can do is, why don't we just multiply both sides by the inverse of this whole thing? So what is that? Well, the inverse, as we've described, doesn't change it from being lower to upper. So we have factored a matrix into lower times upper. So the lower triangular is product of inverses of row ups. Upper is row echelon form. Okay, so we'll stop here. I didn't do an example, which I'll do next time, but with this logic, you should be able to do it. As long as you know how to describe your row operations, you'll be able to come up with this L. So it's just the row operation inverses multiplied nicely in order. Back one slide, sure. It turns out, and you might be able to figure this out, that the product is actually very easy. You don't really need to do much. But I'll kind of spoil that next time with what the little trick is. But okay, I'll stop recording.